I don't have any tape.
Okay, so lines and planes. These are all the things that we could do. I'm not saying that we're going to do all of them. We for sure will talk about parametric and symmetric equations for a line. Relationships with lines. In planes, we can talk about the general form of a plane, sketching a plane, the intersection of two planes, which would be a line. Okay, and then we could also talk about the distance between a point and a plane and the distance between a point and a line. We'll see if we do those or not. Okay, so lines in space. Okay, we can't really talk about three-dimensional slope. We kind of talked about the other day when we were discussing whether or not two lines were parallel or not. Okay. So instead of having a three-dimensional slope, we have what's called a direction vector. Okay, because that vector, if a vector is going in the same direction as our line, right? Then it's kind of calculating what we would think of as three-dimensional slope, right? Over, like, kind of like the ratio of how far you would go in each direction, x, y, and z. Okay. So we are going to talk about a direction vector. Okay. To determine the line, and don't write all of this down, I'll tell you what you need to write down, okay? To determine the equation of the line passing through a point and parallel to a vector ABC, so vector V is our direction vector, we are going to use our knowledge of scalar multiples. So we know that a multiple times a vector is going to be parallel to said vector. So we know that if we have a direction vector and we multiply it by a scalar, we're going to have parallel, right? So what's going to happen to create this? We are going to take x minus x naught, y minus y naught, z minus z naught, and that will be equal to some scalar for each of our components. Okay, so maybe you want to go ahead and write this down right here, and we'll move forward with what we're going to do with that. Okay. So you see like that x minus x naught, y minus y naught, that's kind of our view of terminal minus initial, terminal minus initial, terminal minus initial, where our initial point is the point P that we've been given, and Q is just any point on the line, okay? So vector PQ is parallel to this vector V because it's multiplied by a scalar multiple. And vector PQ we get by taking terminal minus initial, where this terminal point is just this generic XYZ. Okay? So in order to write our equations of these lines, okay, we're going to write them parametrically. We're essentially, let me go back here. If we want each of the components to be equal to each other, right? X minus x naught equals AT, y minus y naught equals BT, z minus z naught equals CT. What? Okay. So if we do that and then rearrange it, we have these parametric equations of the line. X equals x naught plus at. Y equals y naught plus bt. Z equals z naught plus ct. And that is how we would describe our line in 3 space. We're going to describe it parametrically. If, what's in common in all these? T. So if we solve for t, we know that t has to be the same in each equation. So if we solve for t, we have this right here where t equals x minus x naught over a. T equals y minus y naught over b. T equals z minus z naught over c. This is what we call our set of symmetric equations, where essentially we solve for that extra variable t and set them all equal to each other. Okay. So we have parametric equations and we have symmetric equations. Oh. I left my water in the front office.
Get it together.
I know, and my phone.
Double oh no.
It's really a Monday.
It is.
Just another man.
The only
It was like
reason-
Wednesday. Like Mr. Hazarosh was talking about, oh, no, we have
The only
this going
reason
on a
I
week from
think that
today, and I was like, well,
because German-
I definitely thought it was Wednesday.
They play that every Monday.
Okay, so if you may want to write down that x naught, y naught, z naught is the point passing through the line, and this ABC is the vector that is parallel to our line. We've talked about it, but I haven't forced you to write it down. So just so you know where all of these random letters and subscripts are coming from, the x naught, y naught, z naught, I know that you knew it 2 minutes ago, but tonight I don't want you to forget that that's the coordinate that's on our line, and I don't want you to forget that vector ABC is the vector parallel to our line. Okay, so here's our first example. It's very simple, but we always start with simple.
So, aside from over all the things now, we play Monarchs today. For those who don't know, so I suggest you will come and support us. If not, maybe very easy. Very easy to find. Zach, he's the coordinator. Here's what he like. He's like, okay, everybody, you know the theme is tonight. Attendance.
I think more like 45. So that when that sun goes down, it's going to be cold. I hope I can sneak into the press box. I feel good. I'm excited to see all the things on the screen, like the vision board. You know what I mean?
Did you see mine last year?
It doesn't, like on Twitter, it doesn't like actually go through. All I see is that you're holding a book, like, because it's frozen. Like, it doesn't work when he tweets them out. Okay. Okay, so our parametric equations, we're going to take our coordinate 2, 3, -4, and then add our direction vector times t. So we have 2 minus 1t for x, 3 plus 2t for y, and -4 plus 5t for z. Those would be our parametric equations. So, like, if I were you, I would write x equals, y equals, z equals, and I'd write my coordinate, boom, 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 and then I would go through and I'd put these coefficients in for the plus at plus bt plus ct. Okay. If we solve these for t, and I would think about setting this up, and then I would think about what it would look like to solve for t. If we solve for t, we would have x minus 2 divided by -1. We would have y minus 3 divided by 2. And we would have z plus 4 divided by 5. Those would be your symmetric equations. Okay, so the chances of me giving you something this simple are pretty slim. So let's talk about something that I would actually give you in a test scenario. Well, what's more likely?
A polynomial in three-dimensional space.
Okay, we're talking just about lines. What do I typically give you in lines? Like, hey, give me the equation of this line. Here I gave you point and slope. Instead of point and slope, I could give you point and point.
Ooh.
Write these two down. And here's where it gets a little bit hairy, because there could be multiple versions of the same solution.
Oh, that's tricky.
Only if you're grading.
Only for grading, yes.
See, what's gonna end up happening is
And checking your answers. Okay. So, just a little sense of appreciation for your teacher who's grading these. Maybe we can just all be consistent. Just kidding. Okay, so really, it doesn't matter which vector you choose to create out of this, because we're all going to get to a similar place, but it's going to represent the same thing. But just like you would in 2 dimensions, if you have 2 points, you need slope. So, well, we don't do slope in 3 dimensions, we do a vector. So what we need from these 2 points is our direction vector. So I'm just going to treat this as first point terminal, second point initial to get the direction vector. Okay, so if 1, 2, -2 is initial and 3, -2, 5 is terminal, find me my vector. What's our vector? 2, -4, 7. So if our vector is 2, -4, 7, then we can set up our parametric equations. Now here's where it gets kind of tricky. We have 2 different coordinates here. So if I choose this first coordinate, this would be my set of parametric equations. But Darby could decide to choose 3, -2, 5, and her set of parametric equations would look different. That doesn't mean that she is wrong, or I am wrong and she's right. We are both correct. It just would take different t values to get the same coordinates throughout our line. Okay. Basically, if you choose whichever point you choose is saying that that's the value, that's the coordinate you would get when t equals 1. But if we choose different t values, we would still get the same coordinates on the line. Excuse me, did I say t equals 0?
said t equals
I meant t equals 0. Okay. So you could also have x equals 3 plus 2t, y equals negative 2 minus 4t, and z equals positive 5 plus 7t. That would also be fine. Okay. It just depends on what you view as your initial and terminal coordinate. Okay. We could have also gone the other way with our vector. Our vector could have been negative 2, positive 4, negative 7. And then again, our parametric equations would look slightly different. But plugging in random t values, we would still get the same coordinates on the line. Okay? So there's a little bit of flexibility in writing these equations. Does that make sense?
So they're the same thing.
Right. Are you okay with that? Okay. It's kind of like, Gabe,
It's fine, we're good. We can move on.
I was still on time on it. Those two represent the exact same equation or graph, but plugging in t values just get you, like different t values get you different points, but they all match up to be the same points. Okay. Sorry, my brain was already going there. I had to continue.
That's okay.
Okay. All right. How about a plane? We've never gotten to write the equation of a plane before.
It's the Bernoulli principle.
Okay.
Physics.
We've at least talked about the xy plane and the xz plane and the yes.
Planes in space. That's called a spaceship.
Ooh.
Once your plane leaves the atmosphere, it's not a plane.
It's just this
It's
thing.
a spaceship.
Or it's just a bunch of rubble.
Or it's
Yeah.
Wow.
Okay.
I watched
These
Guardians
spaceships
of the Galaxy
instead.
2 yesterday.
Is it planes in space?
Really?
Spaceships. Okay, spaceships is this section.
What's the difference between a spaceship and a space shuttle, Roby?
The shuttles get you there. The ships move around. Yes, exactly.
It is being recorded. Gotcha, I go by here next year.
Please be sick this day next
He needs to purposefully play bass
Instead of teaching.
because we're hilarious.
Okay, did you draw any of that and note that vector n is the normal vector to the plane? What do I mean by normal?
It's perpendicular.
Okay. I don't say orthogonal because that's with two vectors being perpendicular. So we have the perpendicular vector to the plane. Okay. So we're going to talk about, there it is. So for any point Q, do you see it magically appear in the plane? We can make a vector, and it would also be in the plane. And what would be true about PQ and vector n?
It would always be.
They would always be orthogonal, which means what? Their dot product is 0. Okay? So Q is any coordinate in the plane XYZ. It's a general coordinate. We can put it anywhere in the plane. And we can create a vector PQ. And we know that this would also be perpendicular to vector n. So if they are perpendicular, then n dotted with PQ is going to be 0. Which means when you take the vector ABC and you multiply it with a dot product to our vector PQ, which is x minus x naught, y minus y naught, z minus z naught, if they have to multiply to be 0, then A times x minus x naught plus b times y minus y naught plus z times z minus z naught has to equal 0.
Whoa.
And that is how we're going to write the equation of our plane. So what would you need in order to write the equation of your plane?
2 points.
Okay, so you need a point P in the plane. All you need is a point P, and you need the vector perpendicular to the plane, and that's it. Okay, so point P is in the plane, and then vector N, which is ABC, is perpendicular. Okay. Okay. So whatever you need to write down about it, okay, make sure you are notating that x naught, y naught, z naught is in the plane, and make sure you notate that the vector a, comma b, comma c is our normal vector. Okay, and this would be what we call standard form. General form would be when we multiply everything out and write it as ax plus by plus cd plus whatever all those constants add up to be equals 0. Trying to remember how much. There's like so much more to this section than I actually teach. So I'm just trying to get a mental picture of when I stop. But we have a few more things to do. So we're going to do a couple examples. One very basic and one, semi-basic example. And then we'll talk about how to actually sketch these planes or spaceships. I'm sorry. Spaceships.
UFOs. Yeah,
That's
but
what
we,
I mean.
We're trying our best to identify them.
Think about the
But if you identify it as a spaceship, then you can't call it a UFO.
Yeah.
We're identifying.
it's
just-
semantics.
It's either a UFO.
It's an IFO.
We find.
That's an
You should
UFO.
start using that term. Oh, look, there's an IFO. Just an airplane, Jackson. Yeah, I know what it is.
You just throw a pencil
It's identified.
It's like, oh, it's an IFO.
Birds are all IFOs.
How do you know
Unless
that birds
it's
are
like
real?
Okay, this is taking a turn. Go ahead and write down this example.
My dad knows a lot about birds, but sometimes he won't tell me what bird it is. That's not
Birds
true. That
aren't
would be
real.
weird.
We all know that.
Okay, we have a normal vector to the plane, 3, 1, negative 2, and the plane contains the coordinate 2, 3, negative 1. Yes.
Will there be problems where they give us 2 points and then require us to find the normal vector?
You just be patient, Joseph Barkley, because I think I have the example that you want to go through next, okay? All right, this is like, look at the formula, plug numbers in, right? Okay, so standard form, we would write in that we have 3 times x minus 2 plus 1 times y minus 3 minus 2 times z plus 1 equals 0. Plug in the vector for those a, b, c, and then plug in the point for the x naught, y naught, z naught.
So if you were to find the angle of the vector, could you then change all of those by 90 to find the angle of the plane?
Well, it depends on what angle we're talking about. We're in 3 space. So if like,
The alpha, beta, and gamma angles.
yeah.
Okay.
Yeah. Now, if I wanted this in general form, then we could distribute the 3, distribute the 1, distribute the negative 2 to write 3x plus y minus 2z minus 11 equals 0. Okay, so no matter what, if you have your normal vector and your point, you have to write it in standard form. So if I ever ask you for general form, you have to write it in standard form so then you can distribute to get to general form. Yes. Okay, so now let's go to Joe's question. What if you have multiple points? How do we figure this out? Okay. How many points does it take to make a plane? 3. So I would need to give you 3 points in a plane if we're going to be able to create it. Here are 3 points in a plane. Write them down. Okay. It takes 2 items in order to be able to write the equation of a plane. It takes a point and a normal vector. Please brainstorm at your table. How might we be able to get a point and a normal vector for this plane?
You're 100% right. I had to think for a second. I'm like, it is.
So if you have a plane, we've got 2 points in it. You take 2 to make a vector, and you just line up and we'll find it.
I have a good thinking.
Like this would be a vector, and then we can write this and use the dot.
See, what always messes my brain is the fact that like it's perpendicular, but it doesn't look perpendicular.
Think simpler, buddy. Think simpler. What you're doing is not wrong.
This is long.
It's a lot of guessing and checking. Did we ever talk about some way to multiply vectors and our result being perpendicular? Oh, the cross product. I was wondering if we had actually talked about that.
Oh, yeah, you could use that, I guess.
What is that?
You could use that, I guess. Or you could
Remember, if you have vector u and vector v and you take the cross product, then the cross product is perpendicular to both u and v. Do you remember that? Yeah.
See, properties.
So-
I just know how to find it, everybody.
I just guess using
That was
my
evident.
brain.
It was evident.
So we take a vector.
So we need to create 2 vectors. Okay? So if I create a vector from point P to point Q is what I'll name them. If we go from point P to point Q, then we have the vector 3, negative 2, 4. Okay? And, I mean, I think it flows better if you choose one coordinate to be your initial coordinate for both. But it doesn't really matter. Okay? And then I'm going to I'm going to find the vector from P, so we'll call this R. And that vector ends up being 1, negative 3, 6. Okay. We now have 2 vectors that lie in the plane. They both are in there. So in order to find one perpendicular, we can take the cross product. Please do that for me. Take the cross product of these 2 vectors here. And it doesn't matter the order because both u cross v and v cross u are perpendicular. They're just going to be opposite, and that's not a big deal. are you getting
I got the.
negative 14j minus 7k?
I got,
Or positive 14j plus
I
7k?
got 16 J's.
Uh-oh. I have it as 14.
Oh, I see what I did wrong. Yep.
Okay.
I saw. Yep.
Okay, so here again, we're going to have some flexibility because we could have opposite vectors. Okay, I'll look at your work. And it also depends on which coordinate you choose to be your x naught, y naught, z naught. So right now, I am going to choose 1, 2, negative 1 to be my x naught, y naught, z naught. Okay, so here I'm probably more concerned about the general form because the general form will be the same for everybody no matter how they decide to do this problem. It's the standard form that's going to look different from person to person to person.
It's not really that standard, is it?
I see your point. But it's standard compared to all the other standard forms that we have, right? We always see like the x minus x naught in whatever standard form we have, whether it be an ellipse or a circle or the equation of a plane. You know what I'm talking about? So don't be alarmed if I ask you for the general form of a line, because that's going to be the easiest way for us to check that we have the same answer. Okay. Now, negative 2y minus z plus 3 equals 0 would be the same line. Okay. I'm probably going to try to keep my leading coefficient positive. Okay. But if yours is negative, that's not a big deal. I'll just account for that. Okay.
So basically, there's no x element of this. There's no x element of what's perpendicular to the plane.
Well, the coordinates in this plane all have the same x coordinate.
Weird.
Right? Is that what that means? Yeah.
Except they don't. It's the 3 points we were given.
Okay.
It crosses it intersects the x-axis.
It does something. It just does something.
The x's don't matter. Right?
You could have any x.
You could have any x. Yes. Yeah, no, they all have different x's. That was a silly comment.
So the plane is
So it's
angled in a way
parallel
to where
the
all x.
It's parallel to the xz plane. Is that what you're... Okay. Well, how do we even visualize these planes?
You don't.
Okay. We're going to draw them as traces. Okay? So, like, write down x plus 3y plus 4z minus 12 equals 0. Just write it down. Okay. Basically, we can graph intercepts and we can graph the triangle. So if I plug in 0, 0 for yz, then x equals 12. And I plot that point, 12, 0, 0. And if I plug 0 for both x and y, then 4z equals 12, so z equals 3. So we can plot the coordinate 0, 0, 3. And if we plug in 0 for x and z, then I have 3y equals 12, which means y equals 4. So we have the coordinate 0, 4, 0. So here would be the 3 intercepts for our axes, and then you can visualize that plane going through.
So planes are triangles.
Can be.
Well, it takes 3 coordinates to make a plane. So if we draw 3 coordinates, we at least have visual. I mean, just like a line, it goes on forever, but we don't draw it going on forever. This plane is going on forever in each of the directions. Let's see if GeoGebra. I think GeoGebra has 3-dimensional graphing.
Oh
Good.
no.
Hmm.
3-dimensional graph.
Okay, so help me out. That equation that we did with the 3 coordinates. Oh, here. That's not going to be it. Solve it for z from the general equation, and what would it be? Z equals what?
Equals -1/4 x.
I thought I didn't have an x.
The one we just drew.
The one that we did where we had the 3 coordinates and the x disappeared. Like we found the cross product and
Z minus 2y plus 3.
z equals what?
-2y plus 3.
So it doesn't.
That's why. That's cool. Oh, okay. Interesting. Okay. I was really hoping that GeoGebra had 3D, but I don't. Oh. Okay. That looks more like
Axes.
Desmos,
Graph
doesn't it?
4th-dimensional objects.
Maybe.
So I saw an interesting detail about how the fourth dimension would work and how like moving something along would like basically make it more or less.
Well, we tried. Okay.